Okay, so why we actually need all this computer power. I'll try to go maybe slightly into the physics of the problem we solve. It's quantum mechanics. You can see that water molecule is a good example. It has 3 atoms which are connected together like springs, and that's vibrating and rotating. And also there are 10 electrons which are orbiting in some really complicated way. And all this object, if you think of it as a solar system, right? There are these 3 planets or 3 stars and the electrons orbiting around. It would be really difficult motion in order to predict. Computers, really, that's the only way to do this. You can't really sit on the desk and piece of paper and write the solution. You can try. It will take probably age of the universe in order to derive that. So our way of solving it is a pattern examples of other systems that we understand. It's kind of like a Lego. You just need to find the right shapes of this Lego or put them in the right places, because there are really a lot of Lego tiles. Something like 100,000 on average, and that's it's really huge. You can't really put the whole thing into your laptop. And that's why we went to these big supercomputers. It's really unique because it has 14 terabytes of RAM. Can you imagine that? You compare it to 4 gigabytes on your laptop, and this is 14 terabytes. And we can put our Lego tiles. From that, we'll get these billions of lines in our barcode. So we really need the big data. First of all, we need to find a computer where we can put our big data, and also to manipulate this matrix, and also to diagonalize this matrix, so bring it to the form which gives us a solution. And it turns out that there are not only many computers that can do this, there are not many software that can do this. We started from ammonia and water, and also HCN, which featured this week on the BBC regarding the discovery and the characterization of the exoplanets, super Earth. And once then you realize that you need something more. Then you need to go to emeralds, and then we were able to crush this problem from 3 million CPU hours and something like half a year of real calculations. Having this technology or computer software developed that allowed us to reduce the calculation time to a couple of weeks. So it was really huge, because you can really do really important and complicated things once you use the GPU. And that's where we went to Emerald. That was really fantastic, because it completely changed our the perspective, or kind of the idea of the project. We didn't believe that we could manage so many molecules that we selected for this project to do simultaneously within the time required for modelers, because they need this data now, and we need to produce this data now. Nobody actually managed to do this before. Usually the strategy is that you take the molecule and do it, and that in the 1-2 years you produce something that would be applicable. But we were able, because of this computer power that we could get on, we could process all these systems simultaneously. It's very fast. I mean, it's also amazing that how you can just these game computers you can use in real science. And it's really amazing. Some people in the past realized the potential of that, because I don't know that it's not that obvious. There is something game computer that you use at home, and then you can plug it into your supercomputer or plug into your laptop and start doing science. Some people did this, and then they start writing programs. That was amazing. And our next project is to do hydrocarbons. And hydrocarbons, methane is part of hydrocarbons, so we basically think that we now know how methane works. You can't really properly model the chemistry of this exoplanet without knowing how that other species also come together. And we know that hydrocarbons are important for atmospheres of Titan, of Jupiter, and that you can really expect that if methane is there, then all other larger molecules are also there. But it's also interesting that they are all known on Earth, right, in our atmospheres and all industrial applications. Methane is natural gas and the old hydrocarbons. We talk about them every day. We burn them, right? We don't invent new molecules. That's a nice thing about this. That the molecules are there on these exoplanets exactly the same as molecules are here. Not only we can understand them and model what's happening in the atmospheres of exoplanets, but we can also apply this knowledge to some applications on Earth, terrestrial applications, like the burning gases of that practically the same molecules.